So you have probably heard about the Standard Model, the basic building block of particle physics. However, its true nature, relevance, and development is of interest today. In a nutshell, the Standard Model refers to the theory we have about the fundamental particles that make up our universe, their forces, their interactions, and the matter that they make. The model was developed due to the early discoveries in the 20th centuries about the subatomic world, but it was well established until the 1970s. The model is most famously known for presenting a sort of catalog of these fundamental particles. We can divide the particles into two main groups, which are the fermions and the bosons. The fermions are all of the particles known to have mass, and the ones responsible for the formation of matter. The fermions themselves are separated into two groups, which are the quarks and the leptons. For example, a normal proton inside an atom is made up of two up quarks and one so-called down quark. On the other side, we have the bosons. The bosons are non-massive particles that drive the fundamental forces. There are four fundamental forces in the universe, which is electromagnetic force, strong and weak nuclear force, and gravity. Each one of these forces has its own fundamental boson. For instance, electromagnetic force has the photon. However, the model is still incomplete and in development. The graviton, for example, which is the boson that is related with gravity, is yet to be discovered. Moreover, dark matter and baryon asymmetry in the beginning of the universe are still open questions in modern physics. Yet, new discoveries happen inside the Standard Model. For example, in 2013, the Higgs boson was discovered. The Higgs boson is thought to be the particle that gives the property of mass in the universe. Now let's learn some more about fermions and bosons, fundamental forces, quantum phenomena, and some applications of the Standard Model.
Standard Model divides particles into three categories: quarks, leptons, and gauge bosons. Quarks are particles that interact by means of the strong force to form baryons. An example of baryons are neutrons, which are made up of two quarks down and one quark up. Leptons, like quarks, do not interact strongly. Among leptons we have the electron, the muon, the tau, and their respective neutrinos. In the Standard Model, gauge bosons are the ones that act as force carriers between the particles. Among these, we have the photons, which are the mediators of the electromagnetic force. We have the W and Z bosons for the weak force, and the gluons for the strong force. There is also the Higgs boson, proposed in 1964 to account for mass in elementary particles. We still have one force missing, the gravitational force, and we haven't found yet a particle, a boson, to explain this interaction. A common way to categorize these particles is separating them in fermions and bosons, making the differentiation by their spin. Spin is an intrinsic property of elementary particles, just as electric charge. Spin can be thought of as a fixed angular momentum, and it's always a constant multiple of Planck's reduced constant h bar. Normally, the constant is omitted, and we can just talk about having a spin of 1/2, 0. Spin values can be positive or negative. Bosons are the particles with an integer spin. 0 for the Higgs boson, 1 for the photon, gluon, and W and Z bosons, and it is theorized that the graviton would have a spin of 2 if its existence is verified. In the Standard Model, fermions, which comprise quarks and leptons, have a spin of exactly 1/2. Spin is useful because it can be directly related with the wave function, where the particles with an integer spin present a symmetric wave function, in this case bosons. The fermions present an anti-symmetric wave function due to the half integer spin. That has as a consequence properties that can be observed, such as the Pauli exclusion principle, which applies for fermions but not for bosons, which can be at the same place at the same time.
So now we are going to talk about the electroweak model, but first we have to talk and know super well the four fundamental forces that exist in the universe. The first force is the electromagnetic force, the next one is the weak force, and then the strong force, and then the gravitatory interaction. Well, now that we've known the four fundamental forces, we can ask ourselves, what is the electroweak model? Well, the electroweak model is a physics theory that connects two fundamental forces, electromagnetic force and weak force. Well, now we have to define the two forces that connects the electroweak model. The first force is the weak interaction. Well, this type of interaction is between the fundamental particles and is responsible for all the decays of these particles. The best known is the beta decay. And well, this interaction is basically the responsible for transforming mass into speed or into temperature. Well, now we have to talk about the second force that complements the electroweak model. This force is the electromagnetic. Well, this interaction affects electrically charged bodies, and it's the force that is involved in the chemical and physical transformations of the atoms and molecules. And well, this force is manifested through the force between charges with Coulomb's law and the magnetic force. And it's very powerful. Now that we have explained the two forces that complements the electroweak model, we can now understand why this model is very special. And well, the discovery of W and Z particles in 1983 was taken as a confirmation of this theory. But why? Well, the reason is because the theory suggests that a very high temperature where the equilibrium KT energies are above 100 gigaelectronvolts, these particles behaves the same. But what does that mean? It means that the weak force and the electromagnetic force acts like a single force and lead us to the electroweak model.
As mentioned before, protons and neutrons are made of quarks. We can call them nucleons, as we can mention both neutrons and protons. Well, these quarks are in a very confined, tiny sphere, which is the size of a proton of a neutron, and they're moving at speeds quite fast, like very close to the speed of light. And when you have that, tiny particles moving very fast in a very small volume, you need a very strong force, which is called, well, strong nuclear force. Well, the strong force works similarly to the weak force, in the sense that they have charges, sort of charges. You see, the weak force has positive and negative charges, like so. We already know this. But strong force works with 3 charges, and we actually call them colors, but they do not have anything to do with the phenomenon of real color. They're just an analogy. So, they come in the charges of red, blue, and green. Another similarity is how particles interact with each other or interchange energy. In the case of the weak force, we work with photons. In case of strong force, we work with gluons, which are very similar, as they are both massless. But gluons, unlike photons, carry charge, the strong force charge. And this leads to a very interesting property, which is that, unlike the weak force that weakens as you pull things apart, strong force strengthens. Let's use that word, that's kind of confusing. Strengthens as you pull things apart. Think of it as a rubber band. The stronger you pull, the farther apart you pull things, the stronger is the attraction to the inside.
All of these particle and interaction that we've talked about are very interesting, but what's next? What can scientists do with all those developed theories? Well, there are some extremely awesome machines called particle accelerators. This concept started in the late 19th century with the X-ray production discharge and cathodic rays. As these inventions began to evolve over time, physicists began to notice that these artifacts were useful for investigating the properties and composition of matter. At present, the most powerful and world's largest particle accelerator is called LHC, Large Hadron Collider, located at the CERN laboratory in Europe. The main goal of this particle accelerator is, of course, to accelerate the particles, given that when a particle is at high speed, we can analyze it with more detail. We know if we increase the velocity of a particle, its wavelength will decrease. That means that this particle accelerator is like a majestic microscope that will allow us to see inside the matter. Now that we know about the LHC, let's talk about how it works. First, the hydrogen atoms are sent into the dual plasmatron chamber, obviously carefully. Here, all the electrons are ripped off from the atom, leaving only the protons that they are sent into the LINAC 4, where they accelerate and gain an energy of 160 mega electron volts with a velocity of almost 1/3 the speed of light. Then they are sent into the proton synchrotron booster, where this proton synchrotron booster is a 4 superimposed synchrotron that accelerate these proton beams up to more than 90% of the speed of light with 1.4 gigaelectron volts. Then they are sent into the proton synchrotron. I know these names are not quite original, but this is a key component of this machine because it is a ring of 628 meters that has approximately 277 common magnets, including 100 dipoles, that makes the beam round the ring and not crash the walls. At this point, protons will reach almost the speed of light. Consequently, they will start increasing in mass. So they will be sent into the super proton synchrotron, a 7.7 kilometer circumference ring that is able to accelerate protons to an energy peak of 500 gigaelectron volts. Soon, this proton will be able to finally be launched into the gigantic orbit of the LHC. Inside the accelerator, 2 protons with high energy with velocities insanely close to the speed of light will be traveling, one in clockwise direction and the other one counterclockwise. Obviously, they will be separated in tubes kept at ultra high vacuum, guided and surrounded by a strong magnetic force, and that force maintained by superconductive electromagnets. So when they are traveling, they will eventually cross over at specific points, and in these points some experiments take place, like CMS, LHCb, Atlas and ALICE. And yes, Atlas and CMS are the responsible of spotting the Higgs boson back in 2013. So at these crossover points is where scientists wait for a collision, and when a pair of protons finally collide, scientists can reveal what are protons made of. So of course they found that they have neutrons, pions, muons, kaons and neutrinos. And let me tell you that pions, kaons and neutrons are the ones that form hadrons, and that's why the name Large Hadron Collider. Anyways, Large Hadron Collider is a machine of discovery. So scientists use these particle accelerator machines to investigate about the subatomic world, to prove the theories about the Standard Model, to investigate about the origin of the universe, and to advance in other science fields like medicine, astronomy, and geology, and the list goes on and on.